First of all, a couple of lads are going to appear with a ladder in a few minutes, and we're going to see the university in action in getting that screen up to the top, even if they have to just loop it over the top with the string, so then we can have a full 2 boards visible. They've been asked several times to do this, but anyway, today they're getting the ladder. So we'll have an extra bit of excitement in the course. Second, I'm going to spend the last 20 minutes today giving you the opportunity to ask questions that may have come up when you were doing trial exam number 2 or the mock exam, because Thursday is exam number 2. Now don't forget, tomorrow morning you also have additional help. 7:15 in Math 501. On Thursday you have me again at 8 in Math 501. Thursday at 9 o'clock you have Brittany in Math East 241 at 9 o'clock. You have your recitation tomorrow. There will be a quiz. The graded homework is graded homework number 9. Some of you may not have been here last time and didn't pick up copies. I have a few copies left for graded homework number 9. I will post, however, I will post one today for those who don't get one. It'll be posted by about 3 o'clock this afternoon. So that's the information about the exam. What we're going to do before then is I'm going to go over again with you the basic ideas for analyzing systems of autonomous ODEs, and in particular second order systems where we have 2 dependent variables and 1 independent variable. And the feature of this system is that the independent variable doesn't appear explicitly in the equation. Now such equations turn up in many, many different circumstances. They don't have to be linear. In fact, most of the interesting ones are non-linear. For instance, the pendulum. The simple pendulum, if I may just remind you its derivation, you have a hinge, you have a very light stick or a string which can stay straight, you have a ball at the end of it, and we have an angle here which we designate as x. And x will change, the angle that the pendulum makes with the vertical will change as a function of time. Roughly, it'll change according to the rule given by Newton's second law, which says that m times, now this is an angle, so the velocity, the angular velocity connected with x of t is dx by dt. You go ahead. Yeah. I'll work over on this board. Thank you. The angular velocity is dx by dt, but the actual velocity will be L times dx by dt. So the velocity along this direction will be L times dx by dt. Now Newton's second law tells us that the rate of change of the momentum, so we'll make this m, it'll produce a force mg acting downwards, so m times dl dx by dt is equal to the sum of the forces. Here there is only one force because we've no damping. It's the restoring force, which is mg, the component of mg in the direction here, which will be mg sine x. So minus mg sine x. Now the m's cancel out, they're constants, and so I get the equation d2x by dt squared equals minus g over L sine x. We convert this into a system by introducing the angular velocity. dx by dt is y. So y is the angular velocity. And then dy by dt, which is d2x by dt squared, will be minus g over L sine x. Is that clear to everybody? Okay. If you had damping, you would add a term proportional to the, usually the best model is a term proportional to the angular velocity. If proportional to the real velocity, it would be L dx dt. Now, the problem that you've been set for graded homework number 9 is the following. And what it corresponds to is essentially a puck. You have a hill here made of ice. And the ice is so slick, it's frictionless. So I have a puck here sliding on the ice surface. Now, the hill here, if we call this the z direction, and this the x direction, the hill is given by some function of x. That's the shape of the hill. Roughly speaking, this shape, for this case, it's approximately x over 2 minus x to the 4th over 4. But in actual fact, if you derive the equation of motion correctly, which I've done here in these notes, the x here in this situation is not just the horizontal distance from this point, but actually the arc length along here, which we call s. So essentially, these are the equations if we use arc length s for the x and the derivative, or the velocity, along that particular surface, ds by dt, for v, which is our y. So this, in fact, this surface, this thing has real meaning, but you have to interpret the x as the arc length along the surface and the y as the velocity of the puck along the surface. Now, you can sort of figure out, you can see, in fact, then I've given the v as a function of s as arc length to be this s squared over 2 minus s to the 4th over 4. And you can sort of see all the things that can happen. You can have, if the energy isn't big enough, the puck will just slide backwards and forwards in that little basin there. That would be one particular motion. Another one would be if you started down here, give it a puck up the hill, but you don't hit it hard enough, so it'll only get to about here, and then the velocity will become 0, and then it rolls right back down the hill again. Ends up at minus infinity. You have a similar behavior on this side. Give it a shove up the hill, it doesn't quite make it to the top, and it slides back down to plus infinity. Now, there's another possibility. We can give the thing a good belt up this hill, enough to reach the top, to get over that top bump. If it gets over the top bump, and these two bumps are the same height, will it get over the second bump? It will, because the energy it'll gain here, it'll lose is going up here. In other words, its kinetic energy coming down here will be replaced by its potential energy getting up the other side. If it has enough energy to get over this bump, it'll get over that bump as well. Now, if there was damping or friction, it may or may not get over the second bump. So it will get up and over the second bump and end up at plus infinity. And then you have the opposite motion doing the same on this side. So you have essentially 1, 2, this really is the same as this, 3 kinds of motion, and they're separated by what I introduced last day as the separatrix, which is in fact the particular trajectory that takes you from the top of that hill to the top of that hill. It takes you from one unstable point to another. We were able to derive the precise equation in the case of the pendulum. We were able to describe exactly what equation that trajectory satisfied. We were able to write down y equals something of x. In fact, it was y was 2 cosine x over 2. That was when we took g over L equal 1. Now we're, in this case, you are also going to be able to write down exactly what that trajectory is. Now, it's not part of the graded homework, but you will find it's nothing other than 2 parabolas. In the xy plane, the separatrix will be the parabola y is 1 over root 2 times x squared minus 1. That's this parabola. Sorry, that's this parabola. And then y equals minus 1 over root 2 times x squared minus 1, which is this parabola. So in the xy phase plane, you're going to see both of these as the separating orbits for these different kinds of trajectories. So your homework is essentially to explore, to play around with this particular set of equations. You're going to be asked to identify the fixed points. How do you identify the fixed points? You just put the f equals 0 and the g equals 0 and find all the xy pairs that satisfy those 2 conditions. Okay, the fixed points obviously are corresponding to the puck sitting on the bottom and the puck sitting on the top of each of those 2 hills. Okay, so this way of this use of the software plus the analysis gained by just solving this first order equation essentially allows you gain a complete understanding for the behavior of this particular dynamical system. Now, I want to go back and do the pendulum again, because last time, if you remember, I said, let's take units where g over L is 1. So I essentially took away the g over L, so we weren't carrying it along. I want to kind of now redo the problem, what we did last day, but keep the g over L in there. And the reason for this is I want to make a point to you about the importance of always getting dimensions and units correct. Because if you treat an equation not only as equating 2 numbers, but also that the units on each side of the equation have to match, then actually you are able to learn a lot without doing a huge lot of calculations. Now, what we're going to do is first, I'm going to actually derive the equation for the period of the undamped pendulum when it's in a motion that doesn't go over the top. Because once it goes over the top, it's certainly not periodic in this angle, because this angle keeps increasing, or if it goes this way. So we're talking about motions now which swing backwards and forwards like this, and we want to write down an expression for the period of that oscillation. So we're going to go through that calculation. We know from this equation, if we can integrate this equation, we'll be able to write down the solution in the xy plane of the whole family of curves. In other words, the solutions x of t, y of t, of equations 8.1, if we eliminate the t, like we have x equals x of t, y equals y of t, eliminate the t, we'll get x as a function of y and vice versa. So we'll get an equation for y versus x. In other words, following the trajectory in time in the xy plane, those trajectories will satisfy this equation. Now, sometimes we can actually analytically solve these equations, sometimes we can't. In this case, we can, because they're both of them, they're separable. We can get all the x's together and all the y's together. And if I do that, in this case, I'm going to have y dy by dx, sorry, y dy plus g over L sine x equals 0. So it's times dx. Now I can integrate both of those. This is half of y squared plus g over L 1 minus cosine x. I've introduced 1 as part of the free constant, and I call that E. In fact, this is the, if I wrote down the full energy equation, I would have half m times L squared d2x by dt squared. So this is the energy, the total energy, I've divided across by m times L squared. Like if I derive the full energy from the top equation, this is what I would get if I essentially, so this is the energy divided by ml squared. Yes?
How is it going to make the y the constant with respect to g?
How can I put in that?
Yeah.
I just, I mean, I can, this is a free constant. I choose to actually write the free constant as E minus G over L. And so I remove the minus G over L over here as plus G over L. The reason for that is that I interpret this as this is the velocity, this is the kinetic energy, and this is the potential energy. If I think of the position here, this is the bottom of the swing. So the pendulum will have the most kinetic energy here and 0 potential energy here. And the potential energy at this position is the height. And the height is proportional to 1 minus cos x. So it would be, the full potential energy would be mgl times 1 minus cos x. So mgl 1 minus cos x, but we've divided across by m times L squared. So that L gets cancelled by the L squared underneath to leave an L here, and the m gets cancelled. Okay? So like the full energy would be, this is the potential energy, and this would be the, sorry, dx by dt all squared. That would be the kinetic energy. And this would all be a constant, which I'll call curly E. Then if I divide by ml squared, curly E divided by ml squared is this E that I write down here. Okay, so these, now let's just check the units. What is the unit of this guy? It's dx by dt all squared. X is an angle measured in radians, so it is unitless. So what is the units of y squared? It's 1 over second squared, correct. 1 over time squared, whatever units of time you've chosen. 1 over the time squared. What is the unit, what are the units of g divided by L? It's 1 over second squared, because this is distance, or this is acceleration, so it's distance divided by time squared. This is distance, so distance into distance over time squared is 1 over time squared. This energy is the total energy divided by, so we have E is this guy, ml squared. So the total energy has dimensions mass times L t to the minus 2. That's the dimensions of time. That's force, and energy is L times that. And when I divide by ml squared, then that cancels, that cancels. So this E has dimensions 1 over t squared. It's the total energy divided by ml squared. So now, this guy, for different values of E, is simply, it's a set of curves in the xy plane. And we examined this last day for the special case where the g over L was 1. So let's look at the, so this is a set of curves. This is a set of curves parameterized by E. In the xy plane. Parameterized by E means that each curve has its own E. If E is very small, so let's look at the different cases. If E is very small, so it's much less than, if it's E is, let me just write if E is small, because I have to say with respect to what. Then, essentially, this guy, which is always positive, this guy, which is always positive, each of those has to be small. If 1 minus cos x is small, it must mean cos x is close to 1. That happens when x is close to 0, or 2 pi, or minus 2 pi, any even multiple of pi. In particular, we're thinking of the 0. So we're talking about these motions, small motions, down here, just shaken backwards and forwards. Then this equation becomes a half y squared plus a half times g over L x squared equals E. Why? Because cos x for x small is 1 minus x squared over 2. And 1 minus x squared over 2 is just x squared over 2. Now these are ellipses with axes 1 over root 2e and 1 over 2 L over G E. Yes, question?
Could you explain why when cos x is small, it's equal to 1/2?
No, I didn't say cos x was small. What I said is these two things are positive, right? If this is small, each of these has got to be small because they can't cancel each other, right? So 1 minus cos x has to be small. So when is cos x close to 1? At 0 is one place, and 2 pi is another, and minus 2 pi is another. But near 0, this looks like 1 minus x squared over 2. So 1 minus x squared over 2 is just plus x squared over 2. X squared over 2. Okay? So this is the equation just of an ellipse. And what we found when we drew the pictures in the JODE in this y-x plane, that in the neighborhood of the 0, we had an orbit, a trajectory that just went round like that. So, topologically, this is a circle, but when we put back in these units, it's an ellipse with these major and minor axes. Now, when E gets large, we get different orbits. For instance, if E was 2 times, what would it be? E is, this is for, let me see. Yep, the orbit that goes through pi 0, or minus pi 0, what's the E if I want to go through pi 0? Well, if I make this 0, and I make this pi, I make this 1 minus minus 1, so that's 2. So E will be 2 G over L. This is the orbit that goes through pi 0 and minus pi 0. So this was the orbit that here was minus pi 0, and here was pi 0. And this is the orbit that carried us over like that. Or there's another one, of course, down here. Now, if I let E here in this equation be 2g over L, then I get a half y squared equals g over L 1 plus cos x. Why? The minus g over L cos x comes to this side. I have 2g over L here, 1g over L here, so I'm left with a 1g over L here. And this, thanks to your excellent trigonometry teachers, is nothing else than 2g cos squared x over 2. So the orbits then are y equals, you've got y squared equals 4 g over L cos squared x over 2, or each y is plus or minus 2 root g over L cos x over 2.
Is that figure you had correspond to when E is small?
Sorry, no, this is, E isn't small. E is 2g over L.
No, I mean the figure of that, like the graph.
Here. This one, this is for E small. This is for E small. E will lie between 0 and 2g over L in this region here. When it gets up to 2g over L, then we're on this separatrix. Afterwards, if you remember, it just goes like this and so on. So the two curves corresponding to the separatrices are E equals 2 root g over L cos x over 2. That's this guy. And the minus 1 corresponds to this guy. So there's all the separatrices in the plane. Now, our goal is to find, supposing we have an orbit somewhere in here, so it'll go around like this and this. I want to find the period. I want to find the period of that oscillation. All right, let's show you how to get that period. These are the results of the survey I took. This was a rectangle 1 to 1. This was 1 to 1.5. This was 1 to 1.62. This is 1 to 1.75 and 1 to 2. And the aesthetics of this class gave a result that 14 folk liked this one the best, 34 liked this one, 21 liked this one, 17 liked this one, and 11 liked this one. I have to say, when I gave you the survey, I expected the answers to be more, that there'd be more choosing this guy. Does anybody recognize what is the ratio 1.62 to 1?
5.
Right, that's the numerical value. What is it? Is a very, why is it very special and magical?
The Greeks thought it was the most pleasing ratio.
The Greeks thought it was the most pleasing ratio. I want to come back to that point. I think that's very important. I work on flowers sometimes, and I want to tell you something about that. You see, if you have, keep the pendulum in mind, we're coming back to it. But if you have things with the golden, or this golden ratio, so this side is 1 and this side is x. Okay? Now I want to do the following. I'm going to make a square out of the 1, 1. Okay? So in other words, I get that and move it up here, and so this is a square. Okay, so I make a square. Now, what's the length of this bit? X minus 1. Now I claim it would be nice, it would be interesting perhaps, if this rectangle here were similar to the original rectangle. Similar, what does it mean? It means the ratio of the sides of the two. Essentially a rectangle is determined by the ratio of its sides and the length of one side. So I'm saying it would be nice if the longer side over 1, that's in the first triangle, is the longer side over x minus 1 here. They'd be similar. In other words, they're the same shape, it's just a matter of expanding all the areas in equal ways. In other words, I can take this guy, turn it by 90 degrees, expand it all at an equal rate everywhere, and I would get back to the original rectangle. So the x has to satisfy this equation. X squared minus x equals 1. Or x squared minus x minus 1 equals 0. Now, part of this course was solving quadratic equations from time to time. What is the positive root of this equation? Well, its x is root 5 plus 1 over 2, which is what Ryan told us a minute ago. And this is indeed this golden ratio. it turns up in another very interesting context. If I take any two starting numbers, any two, and I get the next one by just adding the two, and then I get the next one after that by adding the previous two, so on. So essentially the rule would be m at the j plus 1 is the sum of the two previous ones. Now, if I divide across by mj, I'll take the ratio mj plus 1 over mj would be 1 plus 1 over mj minus 1. Now, if I take the limit of this, take j bigger and bigger, we'll call the limit x. So this is x is 1 plus 1 over x. So this gives me x squared minus x minus 1 equals 0. Oh! So the ratio of any two of these numbers formed by this rule that you get the next one by adding the last two has the property that in the limit the ratio will be this golden ratio. Now, to your point, why do you think the Greeks certainly said yes, it's something to do with beauty? In fact, the Parthenon, if you look at the face of the Parthenon, the ratio of the horizontal dimension to the vertical direction is indeed very close to this golden ratio. That's why I thought you guys had picked the middle one up here. But I guess you're not Greeks. I think this must be hardwired into us somehow. And the question is, why? It's rather interesting. Apparently, are there any people here who do music seriously? God, you're an uncultured lot. Oh, shush. Pardon me. What you play piano or? Lovely, yeah. Well, you know, a lot of the musical, the octaves, and you know, there's very much a way of putting them in a one-to-one correspondence with the 2, 3, 5, 8, 13. This is the the best known of the Fibonacci sequences. This rule, by the way, generates Fibonacci sequences. Start with any two, and it doesn't matter which two you start out with, you'll get different sequences, but the ratio in the limit will always be the golden ratio. So people have studied musical compositions, Mozart and things like that, and they swear they see elements of the golden ratio in there. It's a very curious thing. Flowers have, if you see a sunflower, I brought one in, and I think who was it counted for me? 55 one direction, 34 the other, yes. And the ratio of 55 to 34, if you work that out, is very close to 1.62. And but for some reason, flowers, I mean, the life of a flower is basically spent in attracting things to spread its seed, isn't it? I mean, it's got a nice perfume, a nice color. So why shouldn't its pattern also be something which attracts birds and bees and insects, so on? If that were the case, then of course we need the notion of how come these special mathematical structures are somehow hardwired, that we somehow recognize, we perceive them as beautiful. I presume beauty, when we perceive beauty, we're getting a long way away from penduli, but when we perceive beauty, I guess it's something you perceive now resonates with some pattern or some idea, something you have in mind that makes something pleasant, pleasurable. Does anybody want to add to this completely out of the thing discussion before I go back to the pendulum? Yes?
Trees grow their branches and leaves in the Fibonacci sequence also. There was like this 13-year-old kid a couple months ago, I think, trying to figure out how to make solar panels more efficient, because when you have them on your roof, they only face at one angle, so the sun only hits them effectively for a very small amount of time during the day. And found that if you place solar panels in a Fibonacci sequence, separating them apart, spiraling kind of up like a tree, it actually improves the
the collection efficiency. That's absolutely right. I gave a lecture a couple of years ago at the American Advancement of Science Society General Meeting, and when I talked about this, a guy came up to me from MIT who actually constructs these panels. Magical, yes?
The human body is supposed to grow as closely as possible to the golden ratio, and each sex has its own specific key one that's supposed to kind of represent vitality and fertility. Basically, for men, I'm pretty sure it's the ratio of the waist width to shoulder width.
I see.
The closer that ratio is to the golden ratio, it's supposed to naturally resonate in women's minds that they're basically able to make babies.
Right. So wait now, if the man has his shoulders to his waist 1.62 to 1, you say the woman is attracted to that.
Yeah,
God, I'm out of luck. I'm 1 to 1. No, but I think you may. That's very interesting. Is that right? Yeah. Well, I hadn't known about that one, but anyway. So now, girls, you know what to look for, and now what do the lads look for?
I can't remember that one. I'm not sure making assumptions.
All right. Very good. Back to the pendulum. Back to the pendulum. Now, I want to solve this equation. This equation I can write as dx by dt, or it's a half dx by dt squared is equal to E minus G over L 1 minus cos x. Now I want to just take the simple case when I'm going to start at an angle x0. And I will let the pendulum go from rest. So the initial conditions are x of naught is x naught, and dx by dt at naught is 0. So this can be all the way up to up here if you like, whatever. This pendulum can really swing back and forth. Then the E is going to be, the initial energy will be, this was 0, it would be G over L 1 minus cos x 0. In other words, it would just have the potential energy of being up here and no kinetic energy. Now, just combine those two together, and I get this to be G over L times cosine x. minus cosine x0. Now I can take the square root. dx by dt is root 2 g over L, the square root of cosine x minus cosine x0, and it's plus or minus. Why? Because when the pendulum is swinging from the x node backwards, the velocity would be negative. I'd have to take the minus sign. And when it's swinging this way, I'd have to take the plus sign. Okay, what I'm going to do is I'm going to start here, and I want to compute the time it takes to get down to here, because the total period will then be 4 times that, just from symmetry. So I'll start up here, or up here. I'm going to compute the time it takes to get to here, and that'll be 1/4 of the total time for one full swing. Okay, so I'll have to take the minus sign because I'm swinging down. So this gives me dt equals plus or minus, well, it's the minus sign because we're swinging down, minus L over 2g dx over the square root of cosine x minus cosine x0. Okay, that's just separable. I'm separating things out, but I'm using the minus sign because I'm looking at just this portion of the motion, that the velocity is negative as this swings back. Now let's integrate this between x0 and 0. So the left-hand side, it'll be 1/4 of the period. T is the period. Okay? And the right-hand side will be minus L over 2g, the integral from x0 up to 0 of dx over cosine x minus cosine x0, square root thereof. And I can write that, take the minus, change the order of integration, and that will be root L over 2g, integral 0 to x0, dx over square root of cosine x minus cosine x0. So now there is a formula for the period of the pendulum. Now I'm going to actually work this out, make it a little bit more simple in a minute. But before I do that, I just want to point out the following. What are the dimensions of t? Seconds, time. What are the dimensions of the integral here? X is radians, it's dimensionless. What are the dimensions of the integral part there? An angle, you're just integrating over dx, which is radians. There's no dimensions. So straight away I know that the period of the pendulum will be the square root of L over g times some number. And that number just depends upon the initial angle. Now actually I could have figured that out at the get-go. And I'll show you how to do that now in a moment. But first I'd like to finish this calculation. Just to simplify things, what I'm going to do is I'm going to write, you love this because this is lots of trigonometry, t over 4 is square root of L over 2g times I'm going to make this naught to x naught, and I'm going to write cosine as 1 minus 2 sine squared x over 2. So this then becomes dx times sine squared x 0 over 2 minus sine squared x over 2, the square root thereof. And we have a 2. So there's another 2 comes out here. That 2, when it comes out from under the square root, will be a root 2, multiply that. So this will be t over 4 is this, so t is twice that. Now, I want to put the x naught, I'd like this naught to pi, or pi by 2, in fact. So I'm going to solve this, I'll let sine x over 2 be sine x 0 over 2 times sine phi. Yes?
I missed that. What did you do to get the 2 out of the square root there?
I ended up, when I took cos x minus cos x 0 with 2 in here and 2 here. Took out the 2, square root of 2, multiplied it by that square root of 2, I get 2 underneath. But I had a 4 over here. 4 over 2 is 2. Okay, now when I substitute this in the equation, when x is 0, phi is 0. When x is x naught, sine phi is 1. So this will be pi by 2. So then this becomes 2 square root L over G, naught to pi by 2, dx will be what? I'll have a half cos x over 2 dx equals sine x 0 over 2 cos phi d phi. So I'll have a 2 sine x 0 over 2 times cos phi d phi divided by cosine x over 2. But cosine x over 2 from here is 1 minus sine squared x 0 over 2 sine squared phi. This guy becomes sine x 0 over 2 times cos phi. So I get bang, 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 bang. So I get just 4 times root L over G, naught to pi by 2, times d phi over 1 minus sine squared x 0 over 2 sine squared phi. Now, supposing I took the x 0 very small. Supposing I took the x 0 very small. What is sine of x 0 over 2 if x 0 is very small? It's x 0 over 2. So you can, when this is very small, this will be small squared. So compared to the 1, this will be very small. So if x 0 is small, this is just 4 times root L over G integral naught to pi by 2 d phi. Now what's that? What's the integral of d phi between naught and pi by 2? Pi by 2. And 4 times pi by 2? 2 pi. Now, is that a familiar formula? But you have the formula for all x 0. Now, as x 0 starts swinging towards pi, x 0 over 2 will be nearly 1, and this guy will be getting very singular. I want you to use MATLAB to draw, so we can write the period of the pendulum as 4 times root L over G times this f of, we'll call it A, which is sine x 0 over 2, where this f is just this guy. This is f of sine x0 over 2. So I want you to graph f of a. You know for a small, it's going to be pi by 2. But I want you to graph it. I want you to get the period of the pendulum when sine x0 over 2 gets up close to 1. Now you can't go to 1 because it'll diverge. But you can go to 0.9. So I'd like you to draw that graph. Now you can actually calculate the full period of the pendulum. Now, I was promising you that really I could have said at the very beginning, there's a way to argue that the period has to depend on L and G in this particular ratio, square root of L over G. I'm going to have to come back to that argument. But it's so powerful and it applies in so many places that it's worth spending a little bit of time. It's called, by the way, this is called dimensional analysis. Just looking at the dimensions of things, you can often write down the various dependencies of certain variables just by the fact that the units have to match. But I promised you 15 minutes because you have an exam on Thursday, and there was a couple of things I wanted to mention. So I'm going to take some questions from you. If you don't have questions, I'm going to mention a few things. But I want to say the following. All of those, everyone taking the exam on Thursday who thinks they will finish early, I'm going to ask to sit in this section here. Where's Bowen? Yes, he was out in 20 minutes the last time. So I don't want these bright sparks interrupting the rest of us. So I think, so what I'm going to ask is if you think you're going to leave the exam early, please sit in this section. It's just that, you know, when you're trying to finish off, you're a little worried, you're trying to calculate and things like that, and people are bustling around you, banging the table and getting, you know, finishing up. It's not conducive to finishing off the exam. So we'll do this very simple rule. If you think you're going to be out early, sit in this section, and then everybody else can know that they will be, they'll have no interruptions until the end of the hour and a quarter. Yes, question?
What are some useful trig formulas?
Actually, on the exam, I have put down a couple of trig formulae, and they're very useful. Whether they're relevant or not is another question to the exam, like. Yes?
So are there any ones that we should know, like?
Yes, you should certainly know the following. Sine squared x plus cos squared x is 1. You should know sine of x is 2 sine x over 2 cos x over 2. All right. Sine 2x is 2 sine x cos x. That easier? You should know what cos 2x is in terms of cosine x and sine x. Cos 2x is cos squared x minus sine squared x, which is also 1 minus 2 sine squared x, which is also 2 cosine squared x minus 1. Yes?
Will there be systems of equations on the test?
Systems of equations. Everything that I've covered up to last Thursday, everything I covered up to last Thursday, up to and including last Thursday, are candidates for inclusion in the test.
So not the second order autonomous systems?
I know, I did second order autonomous systems up to last Thursday, yeah. Certain, not everything about it. You haven't learned everything about it, but you've learned certain things. Yes?
Some questions that were like D4X or DT4.
Very good question. Yeah, I'm glad you brought that up. Yeah, this gentleman reminded me that we had on the trial exam questions which were higher order. For instance, d4 y by dt to the fourth minus y equals 0. Now, you solve these exactly the same way as you do second order, guys. You let y equal e to the rt. Then you get the characteristic equation r to the fourth minus 1 equals 0. The roots of this, it's r squared is 1 and minus 1. So the roots would be r is 1, minus 1, I, and minus I. What would be the general solution then? Y would be a e to the t plus b e to the minus t plus I and minus I gives us c cos t plus d sine t. So that would be the general solution. Now, you guys are super at solving quadratic equations. I have high expectations that you can solve quadratic equations. I have less high confidence when you're solving characteristic equations of higher degree. Therefore, if I ask questions which essentially involve things with higher degree, either it'll be very obvious how to factor them, like here, or else I might, as I think in one of the questions on the trial exam number 2, had a question, I said, here are the roots of the characteristic equation. And I put down things like the following. I said, here are the roots of the characteristic equation. 0, 0, 1, 1 minus I, 1 plus I. I might say then, what's the order of the equation? If there are 5 roots here, it's going to be a 5th order equation. What's the general solution? Well, it'll be a e to the naught t plus b t e to the naught t, which is just, again, 1, plus c e to the t, plus, from here, d e to the t cos t, and e to the t sine t. In other words, I will give you the roots of the characteristic equation, and I expect you to be able to write down the corresponding general solution. Now that's not too far of a reach, is it? Okay? Yes?
Minus I is sine t, just a clarification, right?
No. No. What the clarification is this. Okay. Okay. When we look for solutions like this, and we find roots I and minus I, it means that the two solutions corresponding to this is e to the t and e to the it and e to the minus it. Now, as I've told you, it's impossible. Can you imagine e to the it? Do you know what it looks like? Well, you know it's cos t plus I sine t, but so you know what cos looks like and sine looks like, but it's hard to tell what the composition is like. So, and besides, it's not even real. And we generally are looking for solutions of the equation, which corresponds to real displacements or real currents or charges. So we want a real combination of these guys. The two real combinations of these guys are e to the it plus e to the minus it over 2. That's cos t. And e to the it minus e to the minus it over 2I, that is sine t. Because you can work that out because e to the it is cos t plus I sine t. E to the minus it is cos t minus I sine t. So if you solve for cosine and sine, this is what you get. So the answer, Kathleen, the answer is, it's not that e to the it is the cos and e to the minus it is the sine. It's that the combinations, the two combinations of those two things that make real functions are cos and sine. Okay? Yes?
You know that sheet that had those three equations pertaining to like LRC circuits and then
Yeah.
of course the pendulum and stuff?
Yeah.
Do you have to memorize those equations then?
You certainly know, you should. The question is, do we have to memorize the equations corresponding to LRC circuits and to springs and things like that? The answer is, you have to be able to figure them out. You know the rules. Kirchhoff 1 and Kirchhoff 2, they're very simple rules. So in fact, if I give you any circuit, I would expect you can write down, or any combination of circuits, I would expect you can write down the equations that govern the charges and currents in that circuit. Yes?
The reason you got c cosine t plus d sine t.
Yes.
That's not because e to the I is c cosine t, it's because where you mix all the
Yes.
e to the I t minus I t.
Exactly. And remember the basic idea, the principle, is if you have any two solutions of these linear equations, then any combination, some constant times this one and another constant times this one, is also a solution. And the reason we like cosines and sines is we can picture them easily in the mind. And that brings me to another point. Sometimes you'll find as a solution to your problem is a cos t, say a cos 2t plus b sine 2t. Again, I have trouble picturing that because I know what cos 2t looks like and I can multiply it by a, and I can multiply sine 2t by b, but I don't really see where they reinforce each other and where they cancel out with each other when I add the two together. So what I can do is I can write this as the square root of a squared plus b squared times a over the square root of a squared plus b squared cos 2t plus b over the square root of a squared plus b squared sine 2t. Now, since the sum of the squares of this guy and this guy is 1, I can always choose an angle phi whose cosine is this and whose sine is this. Then cos 2t cos phi plus sine 2t sine phi is another of my favorite trigonometric formula. Gives us that this is a squared plus b squared cosine 2t minus phi. Now I can certainly picture that. I can certainly draw the graph of cos 2t minus phi. It's essentially just the graph of cosine shifted by phi over 2 in time. And this is its amplitude. So it's very useful to be able to write your solutions in this form because what's the whole goal of studying differential equations? It's not to torture you. Okay, with all these symbols and rules, it's for you to be able to go out and understand things, understand natural behaviors of all the systems in biology or mechanics or physics or chemistry, which are well described by differential equations. So it's no use having a solution if you don't get some understanding from it. Okay? You want to be able to picture it. And so we have to try and put our answers in forms where we gain understanding. Any other questions? All right, now let me remind you, Tomorrow, 7:15, Math 501. Thursday, 8 o'clock, 501. Maths 241 East at 9 Thursday. So you have lots of opportunities.